So this section 4 is probably the most important section here in chapter 4, or chapter 2, excuse me. Kind of those first couple of days of class, I had talked about how one of the main things that we're going to want to be doing here in the beginning part of this course is redefining. Can we stop talking, please? Thank you. Redefining sine, cosine, and tangent to move away from like the right triangle definition. So we're going to do a lot of that work here today in section 2.4. And this becomes a really important kind of conceptual basis for things that we'll be doing later. So this is one where you really want to make sure that you understand what's going on and what these new definitions are and how things are working. So in section 3, we defined this angle of rotation. So this standard form angle, where we had the vertex at the origin, the initial side on the positive axis, and then like some terminal side that rotates counterclockwise for positive angles and clockwise for negative angles. What we're going to do now is we're going to move away from defining sine, cosine, and tangent with right triangles using like SOHCAHTOA and define sine, cosine, tangent just using points on the terminal side of these standard position angles. So let's say that I pick some point on this terminal side. I'll call that point P. And that point is going to have x coordinate, or coordinate xy. I'm going to then draw a perpendicular back down to the x-axis. I'm going to call that point M, and then the origin we'll call O. And if we look, what have we just formed here? A right triangle. Yeah, so this kind of triangle that we form here is called a reference triangle. And in particular, what we're going to be interested in is this angle that's formed between the terminal side and the x-axis. I'm going to use the Greek letter alpha to represent that angle. So alpha is like that Jesus fish symbol. And we call that the reference angle. And there's an important relationship that exists between the angle theta and this reference angle alpha, in that sine, cosine, tangent, etc., instead of writing each one of those separately, I'm just going to write trig to represent kind of any of them. So sine, cosine, tangent, etc. of theta is going to be basically the same thing as sine, cosine, tangent, etc. of alpha. Now I put a little asterisk there because there could be some sign difference going on here, but we'll show you how we account for that sign difference here in a few minutes. When I say sign, I mean S-I-G-N. Okay, so let's go back to this right triangle that we've drawn. What does the length for side MO have to be? Okay, let me rephrase the question. How do I plot that point P? If you're just going to be plotting something, going back to like pre-algebra. If you were going to plot the point 5, 7, what would you do? Okay, so if we're plotting the point xy, we're going x over, so that's the length for MO, and going y up, that'd be the length for PM. Is everybody happy with that? So how can we figure out the length for PO then? It's a right triangle, isn't it? So I can use the Pythagorean theorem that I know the hypotenuse squared is equal to the sum of the legs squared. Or really in this case that hypotenuse is the square root of x squared plus y squared. And instead of using that, I'm just going to call that quantity R. So now I am ready to redefine sine, cosine, and tangent in terms of x, y, and r. So sine theta is going to be opposite, so y, over hypotenuse, that's r. Cosine theta is adjacent, that's x, over hypotenuse, that's r. Tangent theta is opposite, that's y, over adjacent, that's x. Cosecant theta is the reciprocal of sine, so it's hypotenuse, or r, over opposite, y. Secant theta is the reciprocal of cosine, so that's hypotenuse, or r, over adjacent, which is x. And then cotangent theta is the reciprocal of tangent, so that's going to be adjacent, x, over opposite, y. So this is our new definitions for sine, cosine, tangent, cosecant, secant, cotangent in terms of some point on the terminal side of our standard position angle. So if you recall from last time, the big advantage of these standard position angles is now I can describe an angle of any numeric value, right? I'm not stuck evaluating or dealing with only angles between 0 and 180 degrees, which we were geometrically. I can now have angles as big as I want or as small as I want. I could go to, positive infinity or down to negative infinity. I can represent all of those angles, right? With this new definition, translating SOHCAHTOA into terms of this point on the terminal side, I can now evaluate sine, cosine, and tangent for angles that are not just acute angles in a right triangle, but for angles of any size, which is a major step forward for us. So let's look at a quick example, a numeric example to kind of make sure we have our bearings. Let's say we have the point -3, 4 that's on the terminal side of some angle theta. And I want to find the 6 trig ratios for theta. Well, I'm going to draw a picture. It's not really necessary to draw a picture, but I think as we're getting started with this, it's helpful to get a numeric or kind of connect conceptually or visually kind of what's going on to the formulas that we're using. So I have some standard position angle. So there's my vertex and my initial side. And the terminal side is on the point -3, 4, so something over here. Everybody okay there? So I can make my right triangle. I know this side is -3 because that's the x coordinate, and this side is 4. These reference triangles are not actual physical structures, so we're going to allow them to have negative side lengths. To find r then, I can just do the square root of -4 squared, or I'm sorry, 4 squared plus -3 squared. So the square root of 16 plus 9, that's the square root of 25, so that's just 5. Everybody's okay with that? And now I have everything I need. So sine theta is y over r, or in the case of our triangle, opposite over hypotenuse. Cosine theta is x over r, or in our case of the triangle, adjacent over hypotenuse. Tangent is y over x, or in the case of our triangle, opposite over adjacent, etc., etc., etc. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. And I'm done. So pretty easy, right? So let's take this a step further now. Let's say we want to find cosine of 150 degrees. Again, not necessary to do this graphically, but again, as we're kind of conceptually getting used to what's going on, let's draw the picture to kind of support what we're doing algebraically. I think that really helps kind of connect the concepts and put these pieces together. So I'm going to start by drawing the standard position angle for 150 degrees. So initial side, and then 150 degrees is like over here. I'm going to make my triangle. Now, what does the reference angle value have to be for this triangle? Mia? 30 degrees. How did we know it was going to be 30 degrees? Well, yeah, straight line is 180 degrees. We've gone 150 already. That gives us 30 left to go. Since that angle is 30, I know this angle must be 60. So what we have here is the 30, 60, 90 triangle. We know the side lengths of the 30, 60, 90 triangle are x root 3, and 2x. And because we're located in the second quadrant, I know that points in the second quadrant the x-coordinates are negative. So I know the adjacent side that represents the x-coordinate here needs to be negative. That's an important detail that we have to make sure that we're being aware of. And then cosine is just going to be adjacent over hypotenuse. And when we reduce the x's, I have negative root 3 over 2. Everybody so far so good? Mackenzie? Well, because the point P in this case is in the second quadrant, so the x-coordinate has to be negative. So that side that corresponds to the x side had to be negative. Okay. So the takeaway here is that I can find the exact values for any angles where the reference angle is a 30, 60, or 45-degree triangle, because I could do a similar thing and make these little special right triangles and find the exact value for any of those things, right? So we're going to do that, but before we do that, we're going to standardize this process a little bit more, because up until this point, when we chose that P on that point P on the terminal side of our standard position angle, it hasn't really mattered where we picked our P, right? We just picked an arbitrary P and it was fine. We're going to standardize that process a little bit, and we're going to pick a P in a very specific way to make the process a little bit more uniform. Come on, you stupid thing. Try that again. Okay. So imagine we have some point P. We're going to pick that P so it's 1 unit from the origin. So as I rotate that point P around the origin, what kind of shape is P gonna trace?
Circle.
It's a circle. So what we're going to do, or what we can say is that all these points that P can occupy are going to be points on this circle with radius 1. We call this kind of circle a unit circle because its radius is 1 unit long. So if we fixed our P for r to be 1, instead of sine theta being y over r, it really becomes y over 1, or just 1. And cosine theta, instead of becoming x over r, it becomes x over 1, or just x. Tangent is y over x. That doesn't involve r, so that just kind of stays the same. I'm not going to write it again. Cosecant was r over y, but r is 1 now. So that'll just be 1 over y. And secant was r over x. And again, r is 1, so that just becomes 1 over x. Cotangent was containing only x's and y's, so that didn't change because it didn't involve the r. So what we're saying is that if I have some point P, that this point is cosine theta, comma, sine theta, because the x coordinate should represent cosine and the y coordinate should represent sine. So we're going to build out our own unit circle for these angles that the reference angle makes a 30, 60, or 45 degree angle. So let's start, and we're just going to do this together. This isn't like an assignment or whatever. It's what I'm doing is in the content library, so you can look at it later. We'll start with 0 degrees, which is the same as 0 radians. And since this point has radius 1, I know this has to be the point 1, 0. Everybody's good there? I'm going to skip around here to 90 degrees, which is the same as pi over 2 radians. This has to be the point 0, 1. I'll skip over here to 180 degrees, or pi radians. This has to be the point -1, 0. And we'll go over here to 270 degrees, which is 3 pi over 2 radians, which would be 0, -1. Everybody okay with how I filled those 4? Okay. So my next spot I'm going to do is when my reference triangle makes a 30 degree angle. So the side lengths here are x, x root 3, and 2x. But I know that the 2x side has to represent the radius of my circle, right? So I know this has to equal 1. So x has to be 1/2. And then x root 3 then would have to be root 3 over 2. Okay. So this side represents my x, because that's how far I've moved over. So this is root 3 over 2. And then this side should represent my y, how much I've moved up. That would be 1/2. This spot over here at 150 degrees also makes a reference angle of 30 degrees. Oh, by the way, 30 degrees is pi over 6. And 150 degrees is 5 pi over 6. So the coordinate here needs to be the same, except since we're in the second quadrant, the x coordinate needs to be negative. And then down here at 210 degrees, the reference angle will also be 30 degrees. That's going to be 7 pi over 6. And since we're in the third quadrant, both the x and the y coordinates should be negative. And also at 330 degrees, the reference angle is 30 degrees. That is 11 pi over 6. And since we're in the fourth quadrant, the y-coordinate is negative. Everybody okay there? Okay. Next up is 45 degrees, or pi over 4. So we'll draw our 45, 45, 90 triangle. And since x has to equal 1, then x would have to be 1 over root 2. So also over here at 135 degrees, or 3 pi over 4, will also be 1 over root 2, but the x-coordinate needs to be negative, and the y-coordinate positive because we're in the second quadrant. Here at 225, or 5 pi over 4, we're in the third quadrant, so both the x and the y-coordinate should be negative. And then here at 315, or 7 pi over 4, we're in the fourth quadrant, so the x is positive, but the y is negative. And then my last situation is 60 degrees. So this is going to be the same as the 30, 60, 90 triangle, except like things are in slightly different locations because I've moved where the angle is, right? So here the x is 1/2 and the y is root 3 over 2. By the way, 60 degrees is pi over 3 radians. And then we'll go ahead and move around our circle. So in the second quadrant, the x is positive and the y is, or the x is negative and the y is positive. And that would be 120 degrees, or 2 pi over 3. And the next spot here is 240 degrees, or 4 pi over 3. Since we're in the third quadrant, the x is negative and the y is negative. And our last spot here at 300 degrees is 5 pi over 3. We're in the fourth quadrant, so the x is positive, but the y is negative. You'll also notice in the content library that I have one where everything is filled out for you, nice and typed out, so you don't have to try to read my chicken scratches or your own chicken scratches. But all this unit circle is just a shortcut, right? Instead of having to do the work that we just did by like drawing our standard position angle, figuring out the reference angles, drawing in that special 30, 60, 90, or 45, 45, 90 triangle, we don't have to do any of that stuff. We can just kind of look up the values off the unit circle. So let's do a couple of examples where we do that, just for you guys to see some practice. So we're going to use the unit circle to evaluate some values here. So we'll do sine of 120. We'll do tangent of 5 pi over 4. And then we'll do cosecant of 390. Okay. So let's just kind of go through how we use this unit circle to look up these values. So sine of 120, the first thing I'm going to do is find the 120 degrees on my unit circle. So there you are. I know that sine is y on a unit circle. So I'm just going to read the y coordinate. And I'm done. Pretty nice. Tangent of 5 pi over 4. So first thing I'm going to do is find 5 pi over 4. I know that tangent is y over x. So that's going to be negative root 2 over 2 over negative root 2 over 2. Which just reduces down to 1. That's all right, my friend. Next thing we'll do is cosecant of 390. Uh-oh. If I go look at my unit circle, I don't see 390 on here. What should I do? Yeah, so what I'm going to do is just find an angle that's coterminal to 390 that is on my unit circle. Since these definitions of sine, cosine, and tangent are just dealing with a point on the terminal side, two angles that have the same terminal side should have the same values for sine, cosine, and tangent. So basically I can just subtract 360 and we'll find the 30 degrees. Cosecant is 1 over y. The y in this case is 1/2. 1 over 1/2 is just 2. Everybody okay using the unit circle to look up these values? Joe?
Where is like 1 over y? Is that like, is y like saying like the opposite?
The y is the y coordinate. 1 over y was the same thing as hypotenuse in a unit circle, which is 1 over opposite,
Okay.
which was our SOHCAHTOA definition. Is that what you're asking?
Yeah.
Okay.
I was just like
Yeah.
making sure.
No, totally fine. I just wanted to make sure I answered your question. So one more example. So here we're going to be asked to find sine of theta if cosine theta is 5 over 7 and cotangent is negative. So not necessary to draw a picture for this, but this is all of ours really first time doing this kind of a thing. So let's draw a picture and make sure just kind of conceptually we're understanding what's going on. So I'm going to start by kind of drawing a picture. Remember, cosine is x over r. So that means I could have a triangle in the first quadrant where x is positive 5 and the hypotenuse is 7. Or I could have a triangle in the fourth quadrant because x is also positive there and the hypotenuse is 7. But looking at the cosine alone, it's not entirely clear which triangle I should care about. The way I'm going to determine that is using this additional piece of information that the cotangent is negative. I remember that cotangent is x over y. In our case, I know the x is 5. So that tells me immediately then that y has to be negative, right? The only way for 5 over y to be negative is if y is negative. So the triangle I want is the blue one, where the y-coordinate is negative. Everybody feel good? To find that y-coordinate now, I'm just going to use the Pythagorean theorem. So 7 squared should equal 5 squared plus y squared. So 49 is equal to 25 plus y squared. Subtract the 25 from both sides. I'll square root both sides. Since we're talking about the length of something, I'm not going to worry about the plus or minus. And I can simplify the square root of 24 by thinking about it as the square root of 4 times the square root of 6. 4 times 6 is 24. Because the square root of 4 just is 2. So I know the y-coordinate here is negative. We established that already, so I'm going to put the negative sign there. And then the value, or the length of that side is 2 square root 6. And now I have everything I need to do sine of theta. So that's going to be y over r, or negative 2 root 6 over 7. Joe?
So why did you have to do like 2 triangles? Because like the bottom one is showing that it's less than 0.
Well, there's two places where x is positive and r is positive. Right? So you're always going to have, from just this piece of information, there's always going to be 2 possible places where you could draw your triangle. The second piece of information should be able to whittle that down to a single location. Now, what's worth doing here is to talk a little bit about where these sine, cosines, and tangents are positive or negative based on their quadrants. So in the first quadrant, x is positive and y is positive. Second quadrant, x is negative, y is positive. The third quadrant, both x and y are negative. And in the fourth quadrant, x is positive, but y is negative. So in the first quadrant, sine, which is y, has to be positive. Cosine, which is x, has to be positive. And tangent, which is y over x, has to be positive. I'm not going to bother with the reciprocal ones because the positive or negativeness carries over to the reciprocal, right? Like if cosine's positive, its reciprocal also has to be positive. And if cosine was negative, its reciprocal would also have to be negative, right? So I don't have to worry about the reciprocal ones. Everybody's okay with me just leaving those off? Okay. In the second quadrant then, sine, which is y, is positive. Cosine, which is x, is negative. And tangent, which is y over x, is positive over negative, which is negative. In the third quadrant, sine, which is y, is negative. cosine, which is x, is negative, and then tangent, which is y over x, negative over negative, is positive. And then the fourth quadrant, sine, which is y, is negative. Cosine, which is the x, that's positive. And tangent, which is y over x, is negative over positive, which is negative. So if I look at the first quadrant, everything is positive. If I look at the second quadrant, only sine is positive. If I look at the third quadrant, only tangent is positive. If I look at the fourth quadrant, only cosine is positive. So what we're going to do is we're going to make a little acronym to help us remember this. So HTPC, or all, at least when I was in high school, we said all silly turtles crawl. You can make up your own little silly thing to remember that. But all this is doing is reminding us which of these sine, cosine, or tangent are positive in a given quadrant. And if they're not positive, the other things have to be negative, right? So if we go back to this problem that we just had done, cotangent is negative in the second and fourth quadrants. Cosine is positive in the first and fourth quadrants. What that tells me is that the angle that I'm building needs to be in the fourth quadrant. So that's where I'm going to draw my triangle. So you can do it that way as well without having to reason through like we did originally. Either way is fine though, you're really doing the same thing. Everybody happy with what we've done? Great. I'm going to stop here.